Let's go into the exam questions. Hello everyone, welcome to my channel. My name is Rafael. I am a electrical engineer, linguist, and bilingual teacher of mathematics and physics from Brazil. And in this video, I'd like to invite you to a discussion on equilibrium resistances and equivalent impedances in both direct current and alternating current circuits. And for this purpose, I selected several problems from the most important examinations for electrical engineers in Brazil. Let's go to the first exercise. Exercise number 1 says, determine the equivalent resistance between points A and B of the circuit. Okay, my friends, this is the exercise. Let's go to the solution. This is a very interesting circuit and a rather dangerous one, and should be used as a warning for beginners. Some people do not notice, but if you inspect it carefully, you observe that there is a short circuit between terminals A and B. If you follow the path of current, you will see the short circuit. Let's follow the path of current. Current from A to B will pass here, 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 and here, and here. Observe that there is no resistance. There is no resistance here, 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 or here, okay? Thus, with this kind of design, if we plug the circuit into a power outlet, a fire may occur. We conclude then that the equivalent resistance is 0. The equivalent resistance between A and B is equal to 0. Alright? This is just to stress and asseverate that electrical circuits can be dangerous if not properly handled. And this is everything for the discussion of exercise number 1. Let's go to the next. Let's go to exercise number 2. Exercise number 2. What is the value of the equivalent resistance of the circuit? This is the exercise. Let's go to the solution. To find the total equivalent resistance of the circuit, we must combine resistances in series and in parallel from right to left until there is only one resistance, okay? This is what we are going to do. Firstly, observe these two resistances here, this 1 ohm resistance and this 3 ohm resistance. They are connected in series, okay? This is a series combination, and the first equivalent resistance number 1, is the series combination between this 1 ohm resistor and this 3 ohm resistor. 1 ohm plus 3 ohms, and this is equal to 4 ohms. Subsequently, we observe that this 4 ohms resistor, resulting from the series combination of this resistor and this resistor, will be in parallel with this other 4 ohms resistor. Why? Because they share two terminals. Whenever two resistors share two terminals, they will be thus connected in parallel. Thus, equivalent resistance number 2 is the parallel combination between two resistors of 4 ohms. And how can we calculate the parallel combination of two resistors? It's the rule of thumb that we use, which is the product over the sum. Thus, it is 4 times 4 divided by 4 plus 4, and this is equal to 2 ohms, okay? Observe now that this 2 ohms here, resulting from the parallel combination between this and this will be in parallel with this 6 ohms resistance, okay? And thus they are connected in parallel, and again we use this rule of thumb to calculate the third equivalent resistance, which is the parallel combination between this 6 ohms resistor and this 2 ohms resistor, okay? The rule of thumb is the product over the sum. Thus it is 6 lots of 2 divided by 6 plus 2, and this is equal to 12 over 8, which can be further reduced to 3 halves. Alright? Now, to finish, we observe that this equivalent resistance number 3, will be in series with this 2 and this 3 here, 2 plus this, okay? So the total equivalent resistance will be the series combination between 3 plus 2 plus 3 halves, and this we find that it is, let's take the lowest common denominator here, will be 2 times 3 is 6, 2 times 2 is 4, and 2 divided by 2 is 1, times 3 is 3. And this is equal to 13 over 2 ohms. Okay? Consequently, the total equivalent resistance of the circuit is 13 halves, or, if you prefer, the total equivalent resistance is 6.5 ohms. Okay, my friends? And this is all for the discussion of exercise number 2. Let's go to the next. Let's go to exercise number 3. Exercise number 3. An electronic device was modeled according to the diagram shown in the figure. The question: what is the value of the equivalent resistance? This is the question. Let's go to the solution. But firstly, let's use some labels to facilitate the understanding. I'm going to call this node A, this B, and this C. Observe that there is a wire connecting points A and C. Thus, all the current flowing from A to C will pass through the short circuit, avoiding the 230 ohms resistors. The current will not flow here. It will pass entirely through the short circuit, avoiding these 2 resistances, okay? Observe now that there are 220 ohms resistors in parallel. The short circuit from A to C makes these 2 resistors in parallel. They share 2 terminals. They share this terminal, and this is common to this, okay? So they are connected in parallel. Therefore, equivalent resistance number 1 is the parallel combination between 20 ohms and 20 ohms. And how can we calculate the parallel combination between 2 resistors? It is the product over the sum, and this is equal to 10 ohms. This 10 ohms resulting from the parallel combination between these 2 resistances will be in series with this, okay? We replace all this by this, and we see that they are in series. Thus, the total equivalent resistance will be 10 ohms plus 10 ohms plus 10 ohms, which is equal to 30 ohms. And this is the final or total equivalent resistance of the circuit, and this is all for the discussion of exercise number 3. Let's go to the next. Let's go to exercise number 4. Exercise number 4. Calculate the equivalent resistance of the circuit if R is equal to 3 ohms. This is the question. Let's go to the solution. Before we begin solving, let's use some labels for better visualization. I'm going to call this C, and this here will be A, okay? Observe that between A and C there is always a resistor R. From A to C there is R. From A to C there is R, and from A to C there is R. And between C and B there is this resistor 2R. In this way, for better visualization, we can remodel the circuit as follows. A resistor, and C. But see that from A to C there are 3 resistors R, okay? Three. And from C to B, 2R. Okay, in this way we can understand better the circuit. Let's begin solving. Let's begin with this parallel combination. Equivalent resistance number 1 is the parallel combination between 3 resistors R. And how can we calculate the parallel combination between 3 resistors? 1 over the equivalent resistance is equal to 1 over R plus 1 over R plus 1 over R. In this way, the equivalent resistance is equal to R over 3. This will be in series with this. Therefore, the total equivalent resistance will be R over 3 plus 2R, and this is 3 times 2 is 6 plus 1 7, 7 over 3 times R. And the exercise wanted us to use that R is equal to 3 ohms. Consequently, the total equivalent resistance is 7 over 3 times 3, and this is equal to, they cancel each other out, 7 ohms. Okay? Thus, the total equivalent resistance is 7 ohms. And this is all for the discussion of exercise number 4. Let's go to the next. Let's go to exercise number 5. Exercise number 5. Determine the equivalent resistance between terminals A and B of the circuit. This is the question. Let's go to the solution. To determine the total equivalent resistance, we will combine resistances in series and in parallel from right to left until there is only one resistance. Observe at the far right, there are 3 10 ohms resistances in series. There are 3 10 ohms resistances in series here. Observe also that there is a 10 ohms resistance in series with a 5 ohms resistance. This is the first observation. Thus, equivalent resistance number 1 is 10 plus 10 plus 10, which is 30 ohms. And the equivalent resistance number 2, 5 plus 10, which is 15. Notice now that we have got two 30 ohms resistances in parallel. We have 30 ohms here, okay, in parallel with these 30 ohms. They share two terminals, here and here. This is common to this and this, the 30 ohms that results from the series combination between these three 10 ohms resistances. Thus, equivalent resistance number 3 is equal to 30 ohms in parallel with 30 ohms, and this is equal to 30 times 30 divided by 30 plus 30, and this is equal to 15 ohms. Next, there will be two 15 ohms resistances in series. Okay, we replace all this and this by this, and this in turn will be in series with this, which is 15. We notice then that there are two 15 ohms resistances in series. Equivalent resistance number 4 is 15 plus 15, which is equal to 30. This 15 here replaces all this with this, and in turn will be in series with this, okay? 15 plus 15 is 30. And this 30 will be in parallel with this. It replaces all this and will be in parallel with this. Equivalent resistance number 5 will be 30 ohms in parallel with 30 ohms. This will be in parallel with this. And again, as we saw here, it is 15 ohms. We can remodel the circuit. It will be reduced to this. And here, instead of 30, it is 15, 30, and 15, A and B, okay? We replace all these by this, and the circuit becomes this. This is in series with this. Can you see these two 15 ohms resistances in series? Equivalent resistance number 6 is 15 plus 15, which is equal to 30. And this 30 replaces this, and observe that it will be in parallel with this 30 here. This 30 will be in parallel with this 30. They share two terminals. Equivalent resistance number 7 is 30 in parallel with 30, and this, as we saw here, is 15 ohms. And this 15 ohms will replace all this and will be in series with this. Therefore, the total of final equivalent resistance will be 15 plus 15, which is 30 ohms, okay? And this is the solution of the exercise, and it is all for the discussion of exercise number 5. Let's go to the next. Let's go to exercise number 6. Exercise number 6. What is the value of the equivalent capacitance between terminals A and B? This is the question. Let's go to the solution. As we did in the previous exercises, we will combine the capacitances in series and in parallel from right to left until there is only one capacitance. Observe that at the far right there are 3 capacitances in series. We combine capacitances in series as we combine resistances in parallel. Equivalent capacitance number 1 will be calculated as the series combination of these 3 capacitances, but when calculating the series combination of capacitances, we use the same manner we use for resistances in parallel, okay? 1 over 30 plus 1 over 30 plus 1 over 30. If we calculate, you're going to find that equivalent capacitance number 1 is 10 microfarad. Notice now that there are 2 capacitances in parallel. This resulting from the series combination between these and these, they are in parallel, but when calculating the parallel combination of 2 capacitances, we do the same as we do the series combination of resistances. Equivalent capacitance number 2 is 10 microfarad plus 20 microfarad, and this is 30 microfarad, okay? Subsequently, we notice that there will be 3 30 microfarad capacitances in series. These will be in series with these, okay? If we replace all these by these, these will be in series with these. 1 over equivalent capacitance number 3 is equal to 1 over 30 plus 1 over 30 plus 1 over 30, and as we already know, it is 10 microfarad. And again, this 10 here will be in parallel with this. And how can we compute the parallel combination of 2 capacitances? We do the same as we do for the series combination of resistors, and thus the total equivalent capacitance is 10 microfarad plus 20 microfarad, and this is equal to 30 microfarad, okay? And this is the solution of the exercise, and it is all for the debate of exercise number 6. Let's go next. Let's go to exercise number 7. Exercise number 7. What is the value of the resistances for the 3-phase delta equivalent configuration of the load shown in the figure? This is the question. Let's go to the solution. The exercise provided us this set of resistances connected in Y and requires us to convert it to a delta. For a three-phase load composed of equal resistances or equal impedances, the following is valid. Z delta is equal to 3 times Zy. Thus, the equivalent resistance of the delta connection will be, we simply multiply this by 3. 3 times 15, which is equal to 45 ohms. Converting it to a delta, it becomes 45, 45, and 45. To pass from Y to delta, we simply multiply by 3 the value of the resistance of the Y to get the resistance of the delta. And this is all for the discussion of exercise number 7. Let's go next. Let's go to exercise number 8. Exercise number 8. Determine the equivalent resistance between terminals A and B of the circuit. This is the question. Let's go to the solution. Observe that due to the design of the circuit, the only move that we can make is to combine the 40 ohms resistor with the 30 ohms resistor. Thus, equivalent resistance number 1 is equal to 40 plus 30, which is 70. This is equivalent resistance number 1. From this point, to further simplify the circuit, we will need to convert the delta connected resistors into a connection in Y. Okay? Observe this. They are connected in delta here. And from the previous exercise, we know that Zy will be equal to Z delta divided by 3. Okay? Z delta is 90. Zy is 90 divided by 3, 30. And this combination becomes this. Thirty, 30, and 30. This circuit here will be redrawn as here is 70 from these two, 70 and 80, and now 30, 30, 30, and 30. And here terminals B and A. Now we can reduce the circuit. Let me clear here for more calculation. In this new configuration, we observe that there are two series connections between a 30 ohms resistor and a 70 ohms resistor. Okay? Equivalent resistance number 2 is equal to 70 plus 30, which is 100 here, and the same here. Equivalent resistance number 3 is 70 plus 30, which is 100. Subsequently, we notice that these two 100 ohms resistances are connected in parallel. We substitute this by 100 and this by 100, and they will be in parallel. Equivalent resistance number 4 is 100 in parallel with 100, and this is equal to 50. And this 50 will be in series with this. Okay, 30 in series with this, which replaces all this. Equivalent resistance number 5 is equal to 30 in series with 50, which is 80. And finally, this 80 that replaces all this will be in parallel with this. The final or total equivalent resistance is 80 in parallel with 80, and this is equal to 80 times 80 divided by 80 plus 80, and this is equal to 40 ohms. And this is the solution of the exercise. We need to understand that initially we can only combine this 40 with this 30 and get 70, but afterwards, after doing this, we cannot do much. And the catch here, the insight, is to convert this delta connected set of resistances into a Y. Okay, this became here a Y, and from this we can reduce it further. I can only see this solution. There will be others, but the other solutions will involve Thevenin or Norton, and this is not what we want. We want to simply use equivalent resistances, and in this case we need to convert from delta to Y. And this is all for the debate of exercise number 8. Let's go to the next. Exercise number 9. A label placed on the base of a lamp displayed the following information: 10 watts and 2 volts. Using this information, calculate the lamp's equivalent resistance and the current it draws. This is the question. Let's go to the solution. Remember that for a purely resistive circuit, the following is true. Power is equal to voltage times current. Assuming that the impedance of the lamp is purely resistive, we find the current. The current will be equal to power divided by voltage, which is 10 watts divided by 2 volts, and we find 5 amps. This is the current it draws, the first result. Likewise, we can use that voltage is equal to resistance times current. From this expression, we find the value of the equivalent resistance. R is equal to V over I, the voltage is 2 volts and the current 5 amps, and this is equal to 0.4 ohms or 400 milliohms. And this is the solution of the exercise, very easy, and it is all for the debate of exercise number 9. Let's go to the next. Let's go to exercise number 10. Exercise number 10. What is the value of the impedance measured across the terminals of the voltage source in the circuit? This is the question. Let's go to the solution. The equivalent impedance measured across the terminals of the source is Z is equal to V over I, and this is equal to the equivalent impedance. The impedance measured across the terminals of the source is equal to the equivalent impedance of the circuit. The equivalent impedance will result from the parallel combination between the resistance, the inductive reactance, and the capacitive reactance. Thus, as they are connected in parallel, the equivalent impedance will be calculated as 1 over the equivalent impedance is equal to 1 over 10 plus 1 over J5 plus 1 over negative J2. We can simply calculate, and we find that if we carry out this division, 1 over Z equivalent is equal to 0.1 ohms minus J 0.2 ohms plus J 0.5 ohms, and this is equal to 0.1 plus J 0.3 ohms. We have the inverse of the equivalent impedance. We don't want it the way it is. We want the equivalent impedance, and then the equivalent impedance will be the inverse of this, 1 over 0.1 plus J 0.3. However, the complex number is in the denominator. We want to convert it to the numerator, and to do this we multiply by the complex conjugate of this number, 0.1 minus J 0.3, 0.1 minus J 0.3. A number divided by itself is 1. We can multiply anything by 1 without altering it. If we continue developing this, we find that it is equal to 1 minus J3 ohms. And this is the solution of the exercise. This is the equivalent impedance. You just need to know how to work with complex numbers to find the solution of this exercise. And this is all for the debate of exercise number 10. Let's go to the next. Exercise 11. When a voltage of 20 volts is applied to a resistor, the joule reading produced is 20 watts. In this way, what is the resistance of the resistor? This is the question. Let's go to the solution. Let's consider this resistor. When a voltage is applied at its terminals, a current will flow, which in its turn causes a heating of the device. This is called Joule's effect. Nevertheless, for any resistor, we know that power is equal to V squared divided by R. This expression can be used to calculate the resistance. R is equal to V squared divided by P. 20 volts squared divided by 20 watts. If we calculate this, we find that the resistance is 20 ohms. Simply, all we need to know is this expression. And this is all for the debate of exercise 11. Let's go to the next. Let's go to exercise 12. Exercise 12. What is the equivalent impedance of the circuit? This is the question. Let's go to the solution. Observe that there are two resistors, two inductors, and two capacitors in the circuit. Thus, the equivalent impedance is given by the equivalent impedance is equal to R1 plus R2 plus JW L1 plus L2 plus 1 over JW C1 plus 1 over JW C2. However, as we do not know the values of the capacitances and inductances, nor the frequency of the source, we can simply sum the impedances. Thus, the equivalent impedance will be 10 plus 5 plus J20 plus J10 minus J3 minus J12. Observe that the inductive reactance is positive and the capacitive reactance is negative. Summing these, we find 15 plus J15 ohms. As we want the magnitude of the equivalent impedance, we proceed as follows. The magnitude of Z equivalent is equal to the square root of 15 squared plus 15 squared, and this is equal to 15 times the square root of 2, which is 21.21 ohms. And this is the magnitude of the equivalent impedance, and this is the solution of the exercise. And this is all for the debate of exercise 12. Let's go to the next. Let's go to exercise 13. Exercise 13. For the circuit of the figure, calculate the parameters of the Thevenin's equivalent circuit as seen by the load. This is the question. Let's go to the solution. Remember that the Thevenin's equivalent circuit is composed of the open circuit voltage and the equivalent resistance. This is the Thevenin's equivalent circuit. Firstly, let's calculate the open circuit voltage, and to do so, we open the circuit at the load. We will open the circuit here at the load. Okay, we are going to disconnect the load and calculate the open circuit voltage, and this is I load, the current that goes to the load. Observe that as the output current is 0 for the circuit is open, there is no voltage drop across the 1 ohms resistor, this current here is 0, for the circuit is open. Thus, there is no voltage drop across this 1 ohm resistor. We conclude that as there is no voltage drop here, VOC is equal to 4 volts, the voltage of this voltage source. We know this already. 4 volts. We need to calculate the equivalent resistance. Subsequently, we set the sources at rest, or to 0 if you prefer. Remember that a voltage source at rest is a short circuit, and a current source at rest is an open circuit. In this way, with the sources set to 0, the circuit will become, this will become an open circuit. And this becomes a short circuit. Due to the short circuit, where the voltage source was, the equivalent impedance will be only 1 ohm. Due to this short circuit, the equivalent impedance is only 1 ohm, okay? We neglect all this, and the equivalent impedance is only 1 ohm. Therefore, the Thevenin's equivalent circuit is, this is 1 ohm. The Thevenin equivalent circuit is 4 volts, 1 ohm. And this is all for the discussion of exercise 13. Let's go to the next. Let's go to the last exercise. Let's go to exercise 14. Determine the value of the equivalent resistance of the circuit shown in the figure as seen from terminals A and B. This is the question. Let's go to the solution. Note that the current source in the middle of the circuit is controlled by the voltage between terminals C and A. In the calculation of the equivalent resistance, controlled sources cannot be short-circuited or opened. Therefore, to calculate the equivalent resistance, we must use an auxiliary source connected to terminals A and B. This auxiliary source may be a voltage source or a current source. We will use a current source in this exercise. This voltage source will be set to 0. That is, we will replace this by a short circuit, and here we will use an auxiliary source. And the voltage here will be Vx. Use some labels. I'll label this current IA. This will be ICA, this will be IC, and this ID. When we use the auxiliary source, the equivalent resistance is Vx over Ix. Let's apply KCL at the node C. Here, remember that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node, okay? Therefore, IC enters the node. IC will be equal to ID plus ICA. ID and ICA leave the node. IC is 0.1 VCA. ID is VC divided by 8 ohms, and ICA is VC minus VA divided by 4 ohms. This is a simple equation that can be easily solved. I will invite you to try in your house. After solving this, we find that, okay, to solve this, observe that this will be 0.1 VC minus VA, and you repeat this, VC 8 plus VC minus VA divided by 4, and we find that VC is equal to 0.545 VA, okay? Subsequently, we apply KCL at node A, okay? The sum of the currents that enter this node has to be equal to the sum of the currents that leave the node. The currents entering this node, Ix plus ICA, and the current leaving the node is IA. Ix plus ICA is VC minus VA divided by 4 ohms equal to IA. IA is VA divided by 4 ohms. Since we know that VC is equal to this, we can substitute VC here, and we find therefore that VA is equal to 2.75 times Ix. And since VA is equal to Vx, observe here that the voltage VA is equal to Vx. Vx is equal to 2.75 times Ix. Consequently, Vx divided by Ix is equal to 2.75 ohms. And this is the solution of the exercise. And this is all for the debate of exercise 14. And it is all for this video, my friends. I hope you enjoyed it and learned from it I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye.